Engineering a compiler, parsers, chapter 3 summary. So, parsers, remember they're the second part of the front end. The front end consists of the scanner that we did last time. The parser is what we're doing this time. This is all part of the compiler. So, what are parsers? Parsers take the words from the scanner and determine whether they're a valid sentence or grammar, right? Also has to arrange the tokens into a hierarchy that represents the code's meaning. So, sadly, finite state automatons are too limiting for this problem. So the tool we have to use is context-free grammars. Context-free grammars, CFGs, they consist of terminals. These are the tokens from the scanner and also just the leaves of the tree, right? Non-terminals, these are variables representing the phrases or structures. For example, expression or block. We'll expand upon this soon. Productions, these are the rules that tell you how to replace the non-terminals, right? For example, the expression could become expression plus term. And then it also has the start symbol, and this is the root of the tree. Here's an example of a context-free grammar on the left and the tree that it would make on the right, right? So expression could become parentheses and whatnot, and it would make this tree for this following string. Well, there's a problem. The problem of ambiguity. If a grammar allows two different trees for the same input, then the compiler doesn't know what to do first. The same string. So if you have this following string 3 plus 4 times 5, using this grammar, you could make the tree in two different ways, right? You could have the plus go first or the multiplication go first. This is bad because it won't know how to read it, right? And there are two ways to fix this. You can, one, rewrite the grammar, create layers of non-terminals like term factor to enforce the precedence. This is a good way. And then also you could choose to write precedence rules for the parser. For example, you could say multiplication always beats addition, right? This is an example of using precedence. You can force it by having multiplication and division lower, addition and subtraction lower, multiplication and division higher, and then parentheses the highest. This will always create a tree the same way, right? And so for example, a plus b times c, that's the example we had above. This is what it will create. This is the tree that it will always create. And this order requires that multiplication be done first with the post-order tree walk. So basically, because addition and subtraction is higher up, it'll do those things, and then it'll do the multiplication lower, and then parentheses the lowest, right? And when you actually do the math for the tree, you would start at the bottom and then do the multiplication and then the addition. So it's always going to be the right order. So there are two ways of parsing. We know how the grammar works, and we know what the tree should look like, but there's two ways of parsing it. We have top-down parsing, which starts with the root and tries to grow the tree downward to match the tokens. The problem with this, though, is that it cannot do left recursion. But there's an easy solution. We just rewrite the grammar to remove left recursion. So for example, the expression becomes expression plus term would just become term plus expression because it can't do left recursion. So this is called an LL1 parser. This is left to right scanning, leftmost derivation, and one token of look ahead. The other, so this Top-down parsing grows the tree downward, and it would find the plus, and then the multiplication, right, it would go down. Well, we have bottom-up parsing as the next, so it'd start at the bottom, find multiplication, and then find the addition. And this is better. This starts at the bottom, at the leaves, and combines them upwards until the root is found. This is better and faster than top-down, and it's the standard for parsers today. Shift-reduce parsing, what it does is it shifts by moving the next token from the input onto the stack, and then it reduces by recognizing the top items and matching a rule to them, and replacing that top item with a non-terminal. And then it keeps replacing the stack over and over until it finds only the root. This is called an LR1 parser, or left to right scan, and rightmost derivation, so it's in reverse compared to just normal, right, the left. And then it has one token of look ahead. So we have to use a bottom-up parser with a context-free grammar. Pretty simple. How do we do that? We got to build a table. Unlike our scanners, using a table for the parser is just required, essentially. Like everybody does. Everybody builds it with a table. They don't construct it by hand. The table is constructed by finding the first A, which is the set of all tokens that can begin with the phrase A. So for example, if I'm parsing an expression and the next token is an open parentheses, do I have a rule that has expression that starts with an open parentheses? And that's pretty self-explanatory. And then follow A is the set of all tokens immediately followed by the non-terminal. This is the look ahead of one part right here, one token look ahead. So follow A, the set of all tokens that can immediately follow the non-terminal A. For example, if expression can be empty, I need to know if I should skip it, right? So basically, the tables are built out of sets of possible next tokens. That's the one-liner for you. And then optimizing the tables. Once the tables are built, if multiple rows or columns do the same thing, you can collapse them into one as an optimization. So you can collapse the rows and the columns. And this is good because a smaller table will obviously be faster, and it'll be faster because it reduces cache misses. And that's all for parsers.